acceleration. Okay, welcome to this lesson on force, mass and acceleration. Please date your work up here. So we've got a nice record of when you did this work. We're working in this area over here. We just finished v squared minus u squared equals 2as, a rather complicated equation. And we're really just going to develop our knowledge of Newton's law. So let's get back to our lesson. Here we go. So start off with so we're going to look at Newton's 3 laws of motion. We've already covered one before, but let's just start off with a thought experiment. Got 2 brand new, lovely, nicely oiled and lubricated cars here. They're both on flat roads. These 2 vehicles, both on flat roads. You and 3 of your friends decide to start pushing them along the road. There's no handbrakes on. So what would happen to both of these objects, and what would be the difference between them? So just take a moment to think about that. Okay, well, I think most people would agree that a small car like a Mini, if you accelerated it, it would actually start to move. It would accelerate. Now you might think in some ways that you're fighting the weight of the car when it starts moving along, but you're not, because the weight of the Mini acts downwards, and we'll also get an equal reaction force on the Mini acting upwards. If you apply a force from behind, then actually you're not fighting the weight, but you are fighting something similar to weight. You're fighting its mass, and it'll take force to change this from stationary to be moving. And you're going to apply a force, and this car hopefully will come up with the word accelerate. As you apply a force, and the longer you will keep applying the force, the more the car will accelerate. And the acceleration really is going to be decided by the force you apply and the mass of the car. Now, if you did the same thing, and I'm going to draw these, I'm going to draw some arrows on here, because maybe this bus is more massive than the Mini. So if you applied a force, well, you still should be able to make it accelerate. But how is it going to be different? Well, if the bus was in good condition and you started pushing it, the force would make this mass move. But it wouldn't move as much, it wouldn't accelerate as much as the Mini, because you are fighting more mass. You can still, even really large objects, as long as you can get rid of things like other forces like friction, everyday forces that stop things moving, you can move very large objects with small forces, with very small resultant force. It just means you wouldn't get very large acceleration. So just similarly with the Mini, much easier to accelerate the Mini if all the people, if there's no occupants, but if the Mini was full and it had 4 people in it, ideally if you were trying to jump start a Mini like that, you'd tell the people to jump out of the car, so you get the speed up, you get the acceleration. So let's have a little look at Newton's laws. There's 3 laws that you need to know about. So the first one I'm going to look at is the third one. And the reason I'm going to look at the third one is because we already did it in forces 1. And this was going back to the idea that if you have any 2 objects and they come into contact with each other, the force of one object and the other must be equal to the force on the other one. But not only is it equal, but it must act in the opposite directions. So there. So a good example of this one is a gun fires a bullet. As the bullet comes out of the gun, why is it coming out of the gun? Because it's had a big force applied to it from the explosion, and so the bullet flies forward. And what will happen to the gun? Well, the gun will receive an equal but opposite force and recoil back. Same with a rocket that's accelerating up into the sky. You remember the rocket is accelerating up, and it's literally pushing air particles down. Which is bigger, the sum of all the forces pushing the air particles down, or the sum of the forces pushing the rocket up? Neither. They are equal but opposite. Okay. I'm just going to sort of really just get into the details of these two laws and just going to explain what they are. Newton's first law. Well, Newton's first law, you may remember when we were doing about Newton's third law, one example I gave of an object with zero resultant force was the Voyager 4 probe that's going out, flying into deep space, just leaving the solar system at the moment. And that object travels very, very fast, but it has no force, it's got no energy left in its batteries virtually. But it doesn't need any energy to travel because actually, if you can get rid of all the other forces, for objects that have zero resultant force on them, they just keep on going at the same speed. That's something not so intuitive when we're on Earth because, things like other forces like friction, air resistance, gravity come into play. So it's very rare that we're in a situation where there's no forces on an object in the Earth. So we have this tendency to think that was very common actually. Aristotle actually came up with it, that objects have a tendency to just go back to their stationary state, and that's what they want to do. He was totally wrong. Actually, what happens is that objects travel at a constant velocity unless they have a resultant force applied onto them. Which sort of takes us to Newton's second law, which says, how do you change the velocity of an object? Well, you apply a force. So, what does Newton's law say here? Well, this is not the formal definition, but let's go with this one for now. When an object has a resultant force applied to it, its velocity will change. Now, what we saw on the bus is the formula that really goes along with this is that if you apply a force, you're going to get a certain acceleration, but you're going to get less acceleration for large masses. In effect, this is what this formula F equals ma is telling you. That, if you apply a force, then you get an acceleration. But clearly, these two numbers multiply together to make the force. So if you have a large mass, then for that given force, you only get a small acceleration. But if you had applied the same force to a small mass, then you're going to get a much larger acceleration. So let's have a little look at here then. Triangle. Who's going to go on the top? This is Newton's second law. F equals ma. F equals ma. Hopefully you're starting to rearrange these yourselves. So we cover up the F, and we can see we get F equals ma. Okay. If we cover up the A, we end up with A equals F over M. And if we cover up the M, we can see M equals F over A. What have we got down here? Just bringing you back. So we have actually already talked a lot about acceleration. And sometimes we get confused. Which acceleration we do? This is the same acceleration that we've come across in v squared minus u squared equals 2as. It's the same acceleration of a equals v minus u over t. It's just another way to calculate it, another way to find it. It's another correlation in the real world of physics that F does equal m times a. So please get that, copy that up into your book, and we'll go through a couple of really simple calcs here. Car has a mass of 1,000 kilograms. What force must the car's engines apply to cause an acceleration of 2 meters per second? Well, we're using F equals ma, so might as well write that down first of all. We've got the mass here, we've got the acceleration, so this is really just a case of plopping the numbers in. F equals ma, the mass 1,000, acceleration is 2. Force must have been 2,000 newtons. A lorry has a mass of 12,000 kilograms. What acceleration is caused by a force of 10,000 newtons? Well, follow the method, please. F equals ma. Now let's rearrange that. So we need to arrange that to calculate the acceleration. A equals F over m. Now we can just pop the numbers in. F is, there we go, F is 10,000 and m is 12,000. 10,000 divided by 12,000. Answer is 0.83. Let's not forget the units. Meters per second squared. Now you have already seen this slide, so I'm only going to go through this very quickly. You have already seen this slide. So what we're looking at here, we are looking at resultant force. So just trying to bear in mind, not all questions are going to be as simple as this. The tricky bit sometimes is trying to calculate the resultant force. The final bit of doing F equals ma. So let's just look at these. 10, 2, that's going to be 8 newtons to the left. Let's try and do these together. 5 and 3, 2 newtons to the right, 4 newtons up, 7 and 2 makes 9 up, minus 4, 5 newtons up, 100 newtons to the right. These totally cancel out. These got 0 resultant force on it, so there's no direction there. 2 and 7 to the left makes 9. There's 15 to the right. 6 newtons to the right. 20 and 10 down and 4 up. Overall, the resultant is down. So if you've got a problem with any of these, so these two 8 cancels out. 3 and 3 cancel out. And we've got a 6 and an 11. So, please go back and look at the resultant force lesson in Forces 1. If you're struggling with this, I don't want to spend too much time because we've already done this one. One thing I will notice about this diagram that I don't particularly like is that all the arrows are the same. And you might remember, sometimes it's useful to draw the arrows as if they represent the sizes, but this is still quite clear what it means. So sometimes some more useful sometimes to draw an arrow where the 20 newtons is twice as long as the 10, but it's just not demonstrated in this one. But that's how they decided to do it. So that takes our, here's another one. One example, we'll just do this one together. So there's a 20 kilogram object. It's got 40 newtons to the right, 100 newtons to the left. What's the acceleration? Well, we're going to do F equals ma. Then we're going to do A equals F over m. So what's F here? Well, F is just the resultant force. 100 minus 40, which is 60. 60 divided by the mass is 20, gives us an acceleration of 3 meters per second. But we haven't finished yet, because acceleration is a vector. 3 meters per second to the left. Can you go ahead and do these, please? You go ahead and do these, please. Okay. Acceleration, A equals 0.5 meters per second squared. We've got a mass of 30. What's the force? Well, start writing down F equals ma. It's always a good place to start. The force, no rearranging required. Just need to put the numbers in. Force is, the mass is 30. Acceleration is 0.5. So that force must have been 50 newtons down. Just the one force on this one. Okay. Second one, acceleration. What we're going to do, we're going to write down F equals ma. We're going to write A equals F over m. Well, what is the force? This one, got to be a little bit careful here because there's no one force. We've got to get the resultant force here. We've got 10 to the left and 5 to the right. So that gives us a resultant of 10 minus 5 divided by 20. So it's 5 divided by 20, which gives us 0.25 meters per second squared. You might have just seen that at the bottom there. Acceleration is a vector, so we're going to make sure we add him to the left to give a nice complete answer. What's the mass of this one? Well, it's got an acceleration of 10 meters per second squared. The forces are quite clearly labelled, 20 to the right, 3 to the left. What's the mass? F equals ma. We're trying to calculate m, so we're going to go m equals F over a. So what are the forces? Well, we've got 20 to the right, 3, so we're going to do 20 minus 3 divided by the acceleration, which is 10, so that's 17 divided by 10. So the mass of this must be 1.7 kilograms. And what's the direction? There is no direction because mass is not a vector. Mass is a scalar. Okay, this is not trying to say fright. This is just saying the force to the right. So this has got an object here. It's 10 kilograms. It's got 10 units to the left. It's got this unknown force to the right. I don't know whether it's bigger. The acceleration is 2. I'm going to assume, I'm going to add, make it a bit more clear. The acceleration is to the right. So it doesn't. You could actually get two solutions to this because I haven't been very clear which way it's accelerating. So tut tut on me. So it's accelerating to the right. I've clarified that for you. F equals ma. So F equals ma. Which is 10 times the mass times 2, which is 20 newtons. So how do you get a 20 newton acceleration to the right? That means the resultant force must be 20 newtons. So it's only by having F right, of having an acceleration of 30, then we can get an accelerate that we can counteract this other 10, which gives us an overall acceleration of 2 meters per second. Because F right minus the 10 must be giving us this 20 newtons. Okay, this is a rather complicated looking diagram. I would suggest this might trip over some A-level students. It's not probably as hard as it looks. It's quite an advanced mechanics question, but let's have a go at doing it. I think really it might be a little bit pushing it to expect you to be able to do this straight away. But this is a sort of mechanics problem. I would hope you might be able to just follow through the working. So let's have a good look at it and read through it. Diagram shows a train engine, that's the red, and 2 carriages on a flat track. So vertical forces are balanced, so we can just ignore all the weight pushing down and the reaction forces pushing up. And so they haven't been shown in the diagram because they just cancel out. The driving force generated from the engine is 12 kilonewtons, so 12,000 newtons. That's the train engine pulling it forward. The engine block has 3.4 kilonewtons of resistive force, and each carriage has 2.4. So we've got this driving forward force, 12,000, but we've also got resistance. And that's because there's all going to be resistance in all the machinery in here and the bearings, which are going to stop. We're going to try and prevent the movement that's required to give this locomotion along in this direction. It's impossible to get rid of. Annotate on each diagram below to show a simplified free-body diagram of the whole train, horizontal forces only, and calculate the acceleration. So hopefully you can see that actually this train has got mass, it's got driving force forward to the left, and it's got resistive forces to the right. So maybe you can have a go and have a look at, try and go step by step to the next page and see if you can complete, see how far you can get on your own to calculating the acceleration of this train, and then I'll go through it with you. So step 1 asks you to try and simplify the forces. Now we've already got rid of all the vertical forces. We're not bothered about the weight and the reaction force from the track because we're just assuming that the track is flat and they all cancelled out. So you might have seen this is quite straightforward. The forward force is actually 12k, 12,000 newtons forward. Slightly more tricky. There was 3 forces pulling it backwards. Did you manage to add them all up? Yeah, it was 3.4k plus 2.4k plus 2.4k. And that gives us 8,200 newtons. So 12,000 forward, 8,200 backwards. Now it's starting to get a little bit easier, isn't it? Now we can just sort of say, well, let's get rid of 2 forces and just replace that with our resultant force. 12,000 minus 8,200 tells us that overall horizontal force is to the left, and we've got a horizontal force of 3,800 newtons. Now we just need to do F equals MA. So F equals MA. But what have we been asked to calculate? Well, not F, we've got F. We know the mass of the train, that was all given in the question. We've been asked to calculate the acceleration. So A equals F over M. Let's put the force in. Force is going to be 3,800. What's the mass? Well, the mass is all the parts of the engine, isn't it? So it's the engine plus the 2 carriages. It's the engine, so it's an engine plus the 2 carriages are all, because the train is going along together. It's not that some parts are accelerating at different speeds to the other. The train is all connected. So this train has a constant acceleration. Do that all together, we end up with 0.927 meters per second to the left. Okay. This is quite a tricky little diagram here. What are we looking at? Annotate the diagram to show the horizontal forces on the last carriage at this instant. Show the extension and the tension in the coupling must be. Well, we know from previous that there's a force dragging it back, and that was 2.4 kilonewtons. 2.4, let's just write 2.4k. But we also know that this is accelerating, don't we? We know this is accelerating at 0.927. We know that because that's what we just calculated, and it must be accelerating because there must be some sort of, there's a tension in this coupling here. I'm going to label it as T. And this carriage is not being pulled forward by the engine directly. It's being pulled forward by the tension because it's joined. Imagine if you were holding hands with someone in this from the middle carriage to the back, you'd literally be that join between those and be pulling it forward. The tension must be bigger than the drag force, or else it wouldn't be accelerating forward. So let's do F equals MA. The sum of the forces, the resultant force, is T minus R. Here's R. This is our resistance force. I've written R here, so that's resistance. Let's just label that R so we know what I'm talking about. Sum of the forces, remember this is the sum sign, is T minus R, and that equals MA. So what numbers can we put in here? Well, I don't know the tension, but I do know that the resistance force here, this resistance force is 2,400. I know the mass of this carriage. The mass of this carriage is 800 kilograms. And I know my acceleration because I just calculated in the last question. It's 0.927. So I can actually rearrange this. I want to add 2,400 to this side to get T on its own. Then I need to add 2,400 over here. So I end up with T equals 2,400 plus 800 times 0.927. And if I do that calculation, I end up with 3142. 3142 is the only value of T when combined with this resistive force, it's going to give us an acceleration of 0.927. So probably more A-level standard, that one, because that is a nice extension question. But if you can follow that well, then I think you're doing very well. Okay, little point I'd like to bring your attention to here. We've actually got 3 formulas for acceleration now. We've got F equals ma. We can get rid of that, and we can change that to A equals F over m. We've got our definition of acceleration, which is A equals v minus u over t. We've also got v squared minus u squared equals 2as. And remember, if you just leave that alone, you divide by 2s. 3 ways to calculate acceleration in forces. So which one do we use? Well, this one is actually, I suppose, the definition of acceleration. Interestingly, this formula is what we use to define the Newton. There's not the definition of acceleration. But the simple answer is whichever one works. All of these are acceleration. All of these are meters per second. All of these are true. And in a given situation, all of them are true at the same time. You are not going to have an object that is not obeying these laws. So it just depends what data you have. It depends what you've been asked for, and it depends what information we have and what we have been asked for. So that is really the skill when you're looking at questions in physics. When you're looking at questions in physics, you're trying to think, what information have I been given? And how am I going to go about finding the answers? Obviously, in a GCSE question, you're always going to be given enough information to get to the answer. Maybe in a real world situation, you need to go and decide what things you're going to measure. You might decide to measure velocities and distances. You might measure velocities and times. You might level forces and masses. They're all going to calculate the acceleration for you. Some of them might be more difficult to work out than others, or measure. Okay, so here we are. 3 different questions, all about to do with acceleration. A car accelerates uniformly from 3 to 30 meters per second. During this time, it travels a distance of 50 meters. So, well, that's the initial velocity. That's the final velocity, and that is the distance. And we've been asked to find what is A. So can you see what the equation is shouting out to us? We've got A, V, U, and S. Yep, it's v squared minus u squared equals 2as. We want to rearrange that for A. The easiest way to do that is have an A on its own. We want to divide by both sides by 2s. So it becomes v squared minus u squared over 2s, which becomes 13 squared minus 3 squared. That's 169. Divided by 2s, s is 100. That's 169 minus 9, 160 divided by 100, which is 1.6 meters per second squared. Question number 2. Well, we've got the mass here. We've got u, we've got v, and we've got t. So we've got m, u, v, and t. And we've been asked to calculate A. Now, they've thrown you a little bit of a curveball here because we've given you m, but they haven't given you f. So you can't use f equals ma. But we have got u, v, and t, so that's plenty. Oh, with these 3 here, we can calculate A. So we don't actually need m, they're just giving you a bit of an extra information. Maybe if this was a 2-part question, after you calculate the A, you can actually calculate the f, but we're not doing that here. So let's put down our formula. What we're going to do is really clearly explain what we're doing. So A equals v minus u over t. V is 20. No, it's not. V is not 20. V is the final velocity is 8 minus 20 over t, which is 0.8. So it becomes 8 minus 20, which is minus 12 divided by 0.8 minus 12, minus 12 divided by 0.8 is 15. 15 meters per second squared. Minus 15 meters per second squared, because it's decelerating. Third question. Well, we've got m again here. We've got it's travelling at, that's the initial velocity. Resultant force of the car is braking. We've got the force. So here we've got F, U, and M. Well, we've got enough information here with the F and the M. We're not given V or S or A here. No, we're not given V or T or S. So there's no real other options here. We're just going to have to use F equals M A. F equals M A. A equals F over M. What was the force? The force was 30,000. There's my force there. That's the mass. Divided by the mass, 1400, which equals 30,000 divided by 1400. The answer is 21.4 meters per second squared. Okay, let's go on to another question. This is about accelerating a ping pong ball, table tennis ball. Calculate the force required to accelerate 3.8 grams to 8.2 centimeters per second squared. Hint, you need to think about units first. Answer to 2 sig figs. Well, what we've got here, I've got M and I've also got A. Okay. F equals MA. Looks like it's going to be the answer. They have given a bit of a heads up here. They've told us to be careful about units. We need to get into SI units. So the first thing to realise is 3.8 grams is not going to be 3.8 kilograms. It's actually 3.8 divided by 1,000 to get into kilograms. If you don't want to do it slowly, you're just moving the decimal point down 3 places. So it's 0.0. I've done that again twice. 0.0038 kilograms. Can you see the decimal place has gone down 3 times? 8.2 centimeters per second squared. Well, that's not quite. You need to divide by 100 this time, so it's not 0.8, it's 0.08, 0.08 meters per second squared. So there's my acceleration. I mean, they're both accelerations, aren't they? One's in centimeters per second squared, 0.082 centimeters per second squared. So now we're just going to do F equals MA. Here's my mass. My mass was in kilograms, 0.0038. My acceleration is 0.082. They're both in SI units. So one is in meters per second squared and the other is in kilograms. So if I multiply them together, I will get SI units back out, which is 0.038 times 0.082, which equals 3.116 times 10 to the minus 4 newtons. Almost finished, but not quite, because I have been asked to do it to 2 sig figs. So it's final answer 3.2 times 10 to the minus 4 newtons. I want to actually 0.0032 newtons. That's the same value. So either one of those is your final answer.